What is up, health enthusiasts? It's Coach Lambie here for Working Weights LLC, your guide to strength, health, and all things nutrition. I'm joined as always by my co-host, Dwayne Ulrich, aka Poppy Dwarrell.
Poppy Dwarrell's in the house, guys.
Today we're talking about Neotame, the artificial sweetener.
Artificial sweetener, that's right.
Yeah. Have you heard of Neotame?
I have only briefly. Before you and I talked about it a couple of weeks ago. I have heard about it. I can't tell you anything about it super intelligently. I'm only familiar with the science about aspartame, but Neotame I don't know a whole lot about. So I'm ready to learn.
All right. I'm an Oompa Loompa today.
All right.
Yeah. So we'll talk about Neotame. So
Neotame.
Our buddy Philip Pape of the Wits and Weights podcast sent me a message, and he was like, hey man, check out this article. See if I can pull it up.
From the Papester.
Check out this article on Neotame. Neotame, an artificial sweetener that's chemically similar to aspartame, may seriously damage the human intestine and overall gut health. Not only does it cause cell death in intestinal cells, but it also damages bacteria commonly found in the gut.
Holy moly.
Yeah, so he's like, do your thing. Give me your opinion. Can't wait to hear on it. And so this article is based on a study, a very recent study. And one of the things that seems to be maybe leading both the author of this and then people who are reading the article to think that well, this may be something new, something to worry about here, and I'm right away, I'm not saying it's not, is because this study used physiologically appropriate levels, so levels that people would normally see in a day-to-day, dietary consumption amount, which is one of the things that we usually will find, is kind of wrong with some of the studies. Is usually they'll have it done in rodents or in a petri dish or whatever, and the amounts that they put in there are usually super physiological, sometimes like 7,000 times the amount anybody would see in a day.
Right.
But this one did not see that. And so the author of this article interviewed the author of the paper here, and the author of the study said this study is the first to show that Neotame can cause previously healthy gut bacteria to become diseased and invade the gut wall, potentially leading to health issues, including irritable bowel syndrome and sepsis, and also cause a breakdown of the epithelial barrier, which forms a part of the gut wall. And so we can get into the study here, but yeah, so they're saying like, basically Neotame, can cause leaky gut, or intestinal permeability is the correct phrase there, and cause irritable bowel syndrome and possibly even sepsis. So, I mean, that's alarming.
Yeah, it's amazing how many products it's in too. I was just doing a real quick search there, and man, it's in a lot of stuff.
Yeah.
So did the FDA well, they did. They took a look at it.
Yeah, they took a look at it. So this is the study in question here. This is in Frontiers in Nutrition. We can see this is April 2024. So very, very recent. Right. And then going through the abstract here, Neotame's a relatively new sweetener. Now, they say relatively new. It also says that in that article that we read. And as I was kind of looking stuff up for Neotame, there's stuff that goes back almost a decade on Neotame. So what they mean by relatively new, I'm not really sure, but maybe just new in the global market. Limited data. So in this study, they use a model of the intestinal epithelium and microbiota to investigate how physiologically relevant exposure of neotame impacts intestinal epithelial cell function, gut bacteria metabolism, and pathogenicity, and gut epithelium microbiota interactions. What a mouthful.
Yeah, it's a mess.
Yeah, so their findings: neotame causes intestinal epithelial cell apoptosis and death. So translation is neotame, the artificial sweetener, causes the cells that create the lining of your intestines to die, basically. Right? They go apoptosis is the process of death, of cell death. All right.
Mhm.
And then also highlighted here, neotame exposure results in barrier disruption with enhanced monolayer leak and reduced claudin-3 cell surface expression through a T1R3 dependent pathway. So here they're just outlining what the pathway is. A lot of people will get caught up on these pathways from in vitro or rodent models, and it doesn't that doesn't mean that neotame or any other thing that you're looking at is causing that pathway of, it could be inflammation. In this case, it's intestinal permeability. It's not causing that path. That is the pathway by which this is happening. Okay. So just as we're learning to read studies here and understand how things are happening, when they describe through blank pathway, they're not saying it's causing that pathway. They're saying that is the pathway by which this thing is happening. All right. And so basically neotame in this model of the intestinal epithelium is causing leakages, right? So permeability, which means that bacteria and other things that are in the intestine can get through those leaks. Stuff that's not supposed to get through can get through, make it into the blood system, and that's where the sepsis thing comes from. All right. So getting into the study here, a lot of these in vitro trials and even the rodent trials are very technical in the way that that everything is worded. And you know, it's kind of on purpose. They're just reporting what they found. Things have to be technical in these things because they're looking for specific pathways and they're looking for specific genes or bacteria or whatever the case may be, right? And so they have to use the Latin terms or the scientific terms for a lot of stuff. So it can be very daunting to read these things and understand them. But going back to how we read a study, if you remember, one of the key things that you can do is just try and tell the story of what happened during this trial, right? And so for this specific trial, we really don't need to be concerned with all of the specific scientific names of things and, you know, all of the various things that people can get hung up on. But basically, what they did here, they took Keiko-2 cells, which are the intestinal endothelial cells, plated on black-walled 96 well plate, which is the Petri dish, for 24 hours, followed by exposure to neotame or the vehicle control, which was water, for a further 24 hours. All right. And then they checked stuff out. So what did they do? They took some cells and they also took some bacteria. They had to get bacteria from somewhere, and that came from, I remember reading it. I don't think I highlighted it, but they got it from bird poop.
Yeah, fecalis and E. coli.
Yeah, E. fecalis and E. coli. So people will be familiar with E. coli. All right. And they put that stuff in a petri dish for 24 hours. Now, this brings up to the question. So I didn't understand 100% of the things in here. All right. And again here, bacterial adhesion assay following exposure to artificial sweeteners for 24 hours. So this is the thing that caught my attention here as I'm trying to put together the story of what happened, is that in order to get the results that they got, the cells, the endothelial cells, had to be exposed to the artificial sweetener for 24 hours. So we might posit the question. So we have two things when we're looking at trials, all right? We have human trials, mouse trials, in vitro trials, and all that stuff. And we have two things. We're looking at efficacy and effectiveness. And efficacy deals mostly with the internal validity of the trial. So we're looking at basically like, is the design of the trial good enough to show us that X caused Y? Okay. And so that's where we come up with statistically significant differences and all that stuff. And then we have effectiveness, which is really, in terms of our own personal lives, what we're really concerned with. And that means, does this translate to some meaningful thing in our actual lives? Okay, so just because we can say X caused Y, and we have enough control and the design is good enough in the trial to show that, there's a statistically significant difference, and that leads us with a high degree of confidence that X is causing Y. Is that difference enough to say that that's going to be clinically meaningful? We would say clinically meaningful in the real world, right? Is that going to give us actual results in our real life? So having these cells exposed to the artificial sweetener for 24 hours, we would have to question, is is that same amount of exposure going to happen in the human intestine? Are intestinal endothelial cells in a human being with a functioning digestive system going to be exposed to Neotame for 24 hours? Right?
Yep.
Okay. So for that, I looked up some stuff, and let me see if it's this one. No, I don't want that one.
So now we're going to talk about people's metabolic system and how long it takes them to offload
Yeah, so now we're going to talk
food
about
products.
Now we're going to talk about how long does it take for stuff to make it through your system, right? So they're in this study, they're talking about intestinal endothelial cells. And so we have a large intestine and a small intestine, right? And they don't specify which cells those are coming from. So, but in normal transit time, so when you eat something, the amount of time it takes to go from point A to point B, so gastric emptying, that's going to be in your stomach, is about 2 to 5 hours. The small bowel, the small intestine, is around 2 to 6 hours. And then the colon, so your large intestine down to your colon, is somewhere between 10 and 60 hours. Okay, so the whole gut transit time is around 10 to 73 hours. And that's going to be dependent on a whole bunch of different variables, right? How much fat you have in there, how much fiber you're consuming, all of these different things. If you just drink a diet soda, that can, or whatever, let's just say a diet soda, some drink, right, with no other food, transit time probably gonna be pretty quick, right? So
Agreed.
here the idea that it's spending 24 hours in one area, we might be able to say that's happening in the large intestine. So here's the other question then. Okay, possibly it's spending 24 hours in the large intestine, so it's being exposed to those cells. Now, it's making its way all the way through that thing. It's not just sitting in one place, right? So at no point in time is any one specific area of it going to be exposed for 24 hours to neotame. Let's just even say that it is. Is that neotame being unchanged? Right? So we have to then posit, okay, how much of this, once it goes to the stomach, to the small intestine, and then into the large intestine, by the time it makes it to the large intestine, how much of that has been absorbed and how much of it has been changed? So we know that aspartame from our previous podcast on this, we know that aspartame gets broken down into its main constituent components, right?
Right.
A couple of proteins and a methanol. So does neotame spend all of its time within our digestive system unchanged, or is it being absorbed, and is it being changed within the digestive system?
So let me ask you a question real quick before
Yeah.
we go on. So at what point, maybe you said it, but I didn't catch it. So at what point is the neotame at its most dangerous to gut health? Is it in its original form, or is it after it's been broken down, deasterized, and changed partially into methanol?
Right. So in this study where it caused apoptosis and cell death, it would be unchanged.
Ah, okay. So that's the good question: is at what point does it become deesterized and methanol? How long does that take in the gut?
Right. Yeah. So that's what we're going to look at now. Okay. So the question of would we see neotame residing in the intestine for 24 hours? Possibly in the large intestine. Now we have to posit the question, is that neotame being unchanged? And is it within the same amount? So within this study in question, they said it was physiologically appropriate doses. Okay. So that means that the whole amount that they put in there would have to stay in there, meaning zero of it, or within some range, it would have to be a large percentage of it would have to not be absorbed into the body in order for us to create the same exposure in humans. Does that make sense? So if I put 100
Yes.
grams of neotame into my petri dish and I leave it sit for 24 hours, okay, that means that 100 grams of neotame produce these results. It caused cell death and growth of certain bacteria and degradation of other bacteria.
Right.
Would we achieve the same results at 50 grams? So if I put 100 grams in there and 50 grams of it, half of it gets dissolved or deesterified or whatever, are we going to see the same results? We don't know. But we need to ask that questions in humans. So we're looking at efficacy, right? So we're concerned about whether or not neotame is going to cause irritable bowel syndrome, leaky gut, and other, terrible things like sepsis. So here we have biological data for neotame, and we're looking at the absorption, distribution, metabolism, and excretion. And so we do have some data in humans. So approximately 20 to 30% of administered dose is absorbed and rapidly converted to the major metabolite, whatever that is, which is deesterified neotame. Right? So 20 to 30% of it is rapidly deesterified. So it's no longer neotame. It's just its constituent components. And a number of minor metabolites. Neotame and its metabolites are rapidly eliminated in the urine and feces. All right, so we have the words rapid. What does that mean? Okay, so we need to see about that because we're concerned about being 24 hours. So our human studies here, So in a study involving healthy men, they were each given a single dose of neotame in a solution. So some of them got 0.10, 0.25, 0.5 milligrams per kilogram of body weight. And I think that transfers fine over to our Petri dish study. And they were given those after an overnight fast. And then what did they find? Maximum plasma concentration was attained approximately a half hour after administration. So they consumed neotame, and then they started taking blood samples, and I'm not sure if this one took the urine and feces samples, but they started taking blood samples, and blood samples of neotame peaked about a half an hour after administration. And neotame was rapidly eliminated with a half-life ranging from 0.61 hours to 0.75. So what that means is that if we were to consume 100 grams of neotame, then the half-life, the elimination half-life means that, let's just call it 3/4 of an hour to be easy here. Within 3/4 of an hour, half of it is gone. It's been eliminated. So we consumed 100 grams. Within 3/4 of an hour, half of it's gone. In another 3/4 of an hour, half of that is gone. So you're left with 25%. So an hour and a half after ingestion, 75% of it has been eliminated. Okay. And then another 3/4 of an hour, you're down to 1/8 of it is what's left. All right. So already we can see that through the absorption and the elimination times of neotame in the human body, we can see this 24-hour period of exposure starts to become a little bit less realistic. Agree or no?
No, I'm agreeing. I'm
Yeah.
in my head. I'm doing math, and I'm
So
thinking about most of the conversation. Most of the conversation is about its degradation, cell degradation. The samples used is really all about the petri dish, and I see that this is using humans, and the half life and how it's being digested. I'm just looking at, there's going to be a very, very, if you did 100 grams, 100 milligrams, right? Was it milligrams or grams? I
I
forgot.
said grams, just 100. Let's just say 100,
Yeah,
100 milligrams. So I'm just using 100 for
yeah,
simple
because
math, right?
100 grams was a lot. So yeah,
Yeah.
100 milligrams, and then but so by the time that gets into the large intestine, your colon, it's man, the number is going to be really small.
Yeah.
I mean, with a
Looking
half
at,
life, so just average. So it takes maybe if it takes an average of like um, maybe as little as 2 hours, 5 hours to get out of the stomach, then what is it, 4 to 6 hours to get through the small intestine,
hmm,
and it's not really exposed to the same type of cell structures for the most part that's in the large intestine, the colon. You're dealing with a really, really small amount. So, I mean, I get it that in a petri dish it's terrible, but uh, the body's expelling it at a rapid rate, and there's that word rapid. So,
yeah.
yeah,
So let's do easy math here. So let's say we consume 100 milligrams, and let's just say the half-life is 1 hour. Okay. So 1 hour after consuming it, you've expelled 50 grams, half of it, right? So 50 grams
right,
left in your system.
right.
Now, whether or not that's let's just say it's in the intestines. All right. So 2 hours later, you're left with 25 milligrams. 3 hours later, you're left with 12.5 milligrams. 4 hours later, you're left with 6.25 milligrams. 5 hours later, you're left with
2 point, yeah, basically 3.
3.125.
Yeah, yeah,
What are we at now? 5 hours?
yeah, 5 hours.
Left with 1.6 ish.
Yeah,
6 hours later, you're left with 0.8. 7 hours later, it's 0.4. 8 hours later, it's 0.2. 9 hours later, it's 0.1. We'll go to 10 hours. 10 hours later, it's 0.05. Let's go to 12, right? Because that's half of 24. So at 12 hours after ingestion, you're left with 0.012
At how many hours?
at 12 hours.
Okay, so you realize what that number means, right? So
Yeah, so it's
point zero what'd you say, 0.012
0.012.
milligrams. That means you have point
Let's
zero
yeah, yeah.
zero zero zero, that's 4 zeros, 12 grams. That's tiny. That's tiny. That's 12 10,000ths of a gram.
Yeah, so I mean it's a factor of 10,000. So if we
Yep.
started out with 100 milligrams and at 12 hours you're left with 0.01, if you take 100 divided by 10,000, that gives you 0.01.
Yep.
All right.
Yep.
So at 12 hours, uh, you have eliminated, you know,
A lot.
so much of this has been eliminated in the urine and feces. Now, actually, this one is within the urine. All right. So the short half-life was supported by the rapid disappearance of neotame from the urine. Now, in order for neotame to be in your urine, that means it can't be in your intestines.
Right.
Right. It has
Right.
to have been absorbed. It has to have made its way through whatever processes it needed to do to
Right.
be put into the kidneys and into the urea.
Right.
Right. So, so already here, the efficacy that this petri dish study has, where the endothelial cells are being exposed to unchanged neotame for the same concentration for 24 hours, not a lot of transfer into what's actually happening in a living human being with a functioning digestive system, right?
Right.
And then so we have another study here. So neotame was put into water basically, and they were given a dose of 18.75 milligrams, approximately 0.25 milligrams per kilogram of body weight. And both of these are small sample sizes, but this is what we have. Blood was taken, and up to 168 hours. All urine and feces were collected for 12 hours. So it always gets me, the urine and feces trials. Like, how would you?
Let's not talk about it.
I
Let's
would
not talk
not.
about it.
I would not be interested
Don't,
in doing
don't,
either side of that.
no,
Yeah.
no. I don't even want to talk
Right.
about
So they were collected
that.
12 hours before dosing and
Yeah.
at additional predetermined times up to 168 hours. All right. So 34% of and in this study they labeled the neotame with radioisotopes, right? So we can track it. Okay, so 34% of the radio label neotame were eliminated in the urine, and 63.7 was eliminated in the feces. And that was complete by 96 hours after dosing. So neotame was rapidly absorbed in about the same 0.4 hours. All right. And rapidly cleared from the body with our half-life of about 0.6 hours. All right. So even so our math that we did at 1 hour, we would actually see that result within 6 hours. So, and most of it is converted to deesterified neotame. So mean concentrations of deesterified neotame in the plasma peaked at 1 hour after dosing and were approximately 2.5 times greater than mean peak concentrations of neotame. So, what else do we got? Our neotame and deesterified neotame were detected in the urine at 3.3%. 8 hours after treatment, and 24%, 72 hours after treatment of the administered dose, respectively. very small amounts of radioactive components other than neotame or deesterified neotame were detected in the urine, and unchanged neotame was not detected in feces. Okay, so see if I can get back to our study here. All right, so as far as, well, that's not the one we want. That one. Where are you? Okay. So as far as 24-hour exposure to unchanged neotame, is that actually happening within the human digestive system? And the answer is no. Vast majority of it is being absorbed very quickly, and we're also eliminating it at a very quick rate. And then in the trial where they actually looked at whether or not it was an unchanged or changed neotame. So changed meaning that it had to go through a process of degradation, right? It went through the process of deesterification.
Right.
So it's no longer unchanged neotame. So unchanged neotame is not found in feces. So even if it is staying, whatever concentrations are staying in the intestine and making it through, they're not being absorbed into the body and it's just being excreted, it's being changed. It is an unchanged neotame that we're looking at here.
Yeah.
All right. So
yeah.
So within this cell culture study here, some things going forward for people to look at when you're looking at these types of studies. One, try and tell the story, right? Even if you don't know all of these words here, so they spell some of this stuff out. So E fecum, you don't know what that is. They spell out E. coli in there too. And then Keiko2 cells, you don't know what that is. You can Google it. But just try and tell the story, right? And then start asking the question. So for here, the 24-hour thing peaked to me, right? So 24 hours. So is this sitting in our gut for 24 hours? Is that what it's doing? And the answer is no.
Right. Right. So another question that I have is, can anyone explain or describe or identify the toxicity of 1 gram? So, for example, there are substances that are primarily man-made that just a gram or even a tenth of a gram has a toxicity that is so great that it could cause death or serious impairment. So what is the toxicity level of a gram of neotame? Can anybody tell us that?
Yeah, so neotame, I think if I looked it up, it's similar to aspartame. So aspartame is 40 milligrams per kilogram of body weight per day.
Mm-hmm.
That's the ADI, the advisable daily intake. And the ADI is usually set 100 times lower than our no observable adverse effect level. So it would be 4,000 milligrams of aspartame is where we would start to see observable adverse effects.
Right.
Yeah. And so so for this study, I can see how this can get people because they didn't use, 7,000 times the ADI in this in order to achieve it. And that usually is one of the major factors when we look at these things and, somebody go, oh, a new study says this thing is causing, irritable bowel syndrome. And we said, well, it's 7,000 times the ADI. Well, in this one, they used, below the ADI. But the problem is that the length of exposure, the amount of time that the cells were exposed. And it doesn't even count the fact, that you have cell turnover that's happening. So cells die and new cells are created in the intestine. I don't think that's a super fast process, but there's a whole bunch of things happening in the human body that are not happening in that cell culture. And the exposure to 24 hours is the thing that that the efficacy or the effectiveness of this, so whether or not this actually translates to something in human beings, turns on that 24-hour exposure, right?
Yeah.
And yeah, so it's very easy for people to to uh, run away with their thoughts on certain things. And I found this as I was doing some research, and food additives, gut microbiota, and irritable bowel syndrome, a hidden track. So within that article that we read, it showed, or it said something about gut dysbiosis, and you'll see gut dysbiosis labeled a lot of times in these studies where people are using them as evidence that something is causing gut issues in human beings. So when the term gut dysbiosis is used in a study, it doesn't mean what people are taking it to mean is that it's a bad thing. It just means that there is a change that happened, right?
Yes.
And so people will read something, and authors of these studies will run away with this stuff too. So in this one, I have highlighted here. So these microbial changes could exacerbate the gut symptoms associated with IBS, such as visceral pain, low-grade inflammation, and changes in bowel habits. All right. So I've highlighted could in red here, which means they don't know. It could.
Right. But it's just based on, honestly, that's just based on what's in the petri dish. But I'm
Mm-hmm.
jumping ahead of you. I know I am. But just looking at that sentence, these microbial change could exacerbate, doesn't say
Exacerbate.
cause, it could just make it worse. The gut
Yeah,
symptoms associated with IBS. So someone already has IBS, such as
correct.
visceral pain, low-grade inflammation, and changes in bowel habits. And I can't wait till you get to the red sentence down, but I'll wait for you.
Yeah. So just dealing with this sentence right here, people will read this sentence and take
Yes,
away from that these
it
food
does.
additives are causing IBS. No, that's not
Yeah,
what that sentence says. It says it
correct.
could, which means there's a possibility,
Right,
but they don't have anything to support,
right,
that what they're saying. It could exacerbate, so it could make worse things that are already happening.
right,
So they
right,
are
right.
not saying that's a healthy individual without IBS is going to develop IBS. They're saying that people who currently have IBS,
Yep.
these things might make those symptoms worse.
Worse. Absolutely.
Yeah. And
Absolutely.
so going on here, even if most studies have been performed in animals, which most of them have, and human studies are required, which they are if you're going to make the claim that artificial sweetener causes X disease in human beings, we're going to need human studies for that. Many artificial sweeteners, emulsifiers, and food colorants could represent a potential hidden driver of IBS. And then consequently, food additives should be preventatively avoided in the diet as well as dietary supplements for patients with IBS. I highlighted that sentence in red. So let me translate what this abstract says. It says, we have zero evidence to suggest, or maybe not zero, but we have a very, very small amount, very, very low certainty that any of these things cause gut dysbiosis or IBS or any of these other disease-related outcomes in human beings. We don't have the evidence to support that it causes those. However, we're going to go ahead and just recommend that you avoid them anyway. And that's where people are running away with this stuff.
Yes.
So,
Yes. Yes.
semantic analysis, when you read stuff, sometimes I have to read something 5 or 6 times So I could, read this sentence, pass over it, and you could easily come away with, oh man, this is causing IBS. This is causing these symptoms in IBS. But when you go back through it and you read it a few more times and you actually understand, and we see the word could, exacerbate, those are key words here that show us, okay, it's not causing the issues, but maybe if you have the issues already, it may make those issues worse. But don't let your imagination lead you to make logical leaps to get to conclusions that aren't supported here. All right. And even so, all of this science, and we've done artificial colors, we've done sweeteners, we've done, I don't know, even other additives. It just isn't there, right? The data just isn't there to support the notion that these things are causing any of these diseases. It's not there,
Right.
right? And
Right.
people
Right.
are just they're putting the cart before the horse when they start making these recommendations here. And they'll even
Right.
admit within the scientific literature here, these sentences admit they do not have the evidence to support this last sentence in red. They don't have the evidence to support it.
Right. Even at that though, the consequently is like, so in conclusion,
Yes.
we're saying basically it says if someone with IBS, you need to be careful of additives, food additives, blah, 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 into your diet. So let's just talk about for a second, just for a second, things that exacerbate people, IBS symptoms of people who have IBS. Dairy products, gluten,
Mm-hmm.
vegetables, legumes,
Mm-hmm.
beans, chocolate, rice, spicy foods, whole grain, carbonated sodas, chips and cookies, allium vegetables. There's a couple more. So if you have IBS and there are people, there may be somebody listening to us or watching us, is that they may have IBS. Well, you already have to be careful of what you eat. And so, but does that mean that the evidence is there for Neotame to cause you horrible IBS symptoms? Well, they don't know. There's no knowledge of it. It's just like you said that those are scientific sentences that just are like, hey, well, we looked at it, but we don't really know. But we don't want to look stupid because we have a doctorate behind our name.
Mm. Yeah.
That's
And
bold. That's
yeah.
bold. Somebody's gonna say something about that. But just look at the study and do the math. They don't really know. They don't really know. So odds are no.
They're making the recommendations despite
Yes.
not in light of the evidence,
In
despite
spite of it. Yeah.
there not
Absolutely.
being evidence. They're making the recommendations. Um,
Absolutely.
so you're going to get that a lot from news articles, blog posts, social media influencers who will read things like that, read that last sentence, and run away saying, "Oh, well, you need to avoid these things because they're causing all these issues." Well, I'm afraid not.
No. Yeah.
Okay, so Neotame, is Neotame possibly worse than aspartame? Possibly. I don't think that the study that we looked at today shows really anything other than if you expose endothelial cells to Neotame for 24 hours in a petri dish, they die.
Yeah.
However, I feel like if you were to expose endothelial cells in a petri dish to 24 hours of who knows what,
Jalapenos.
you're still gonna,
Jalapenos.
yeah, you still may see them die. Yeah. So,
My only question out of all of this, my only question out of all of this is who felt they needed to make something that's 7,000 to 13,000 times sweeter than anything else they have? What?
I don't know that they necessarily
Why
like
would you need to do that?
uh well, I mean to replace sugar.
Okay, but 7,000 to
Yeah,
13,000
I don't
times.
I don't know that it comes out being that they go into the process looking to create something that much more with that
Oh,
much more
so they figure
sweetness.
out a
It
process and it
just
just happens to be that much more.
Yeah.
Okay.
Yeah.
Okay. So in my mind, I
Most
I
great.
relate that to in my mind I relate that to the guy that's growing peppers that nobody can eat.
Yeah. So we looked up how when we did the artificial sweetener, I don't remember exactly which one it was, but it was kind of like it's just discovered. Most great discoveries are by accident, right?
Yeah.
And so it's just by accident that this guy discovered that the process of whatever he was doing with these chemicals, I think it was coal tar or something like that.
Yeah.
Um, and ended up with some of it on his hand and licked it, and it ended up being sweet. So I don't think that people set out to make something that is 10,000 times sweeter. It's just
Okay.
oh well, we can actually make a sweetener that doesn't have any calories or has very, very little calories. And it just ends up being that much times sweeter, which is to our benefit because we get to use 10,000 times less.
Well, that's true. That's true. Okay,
Yeah.
I get it. I get it. Well explained and received. Good job.
Yeah. So you know what I mean? So you're reducing calories, you're reducing area under the curve for glycemic loads on people's endocrine systems, and then we're exposing people to something 10,000 times lower the amount than they would be seeing of the sugar. And as far
Right.
as the human outcome data goes, it's generally good stuff. It's really, really only good stuff. So we see when people switch from sugar sweetened beverages to artificially sweetened beverages, we see improvements in weight and body composition. We see improvements in diseases like diabetes,
Yeah.
glucose control,
Yeah.
uh,
Diabetes was the first thing on my mind.
and
Yeah.
we see improvements over water. We see those
What?
improvements. Yeah. So we see greater weight loss in artificially sweetened beverages than in water. So if you
Wow.
substitute sugar sweetened beverages with artificially sweetened or water, you'll see greater weight loss in the artificially sweetened beverages. We also see better glycemic control in artificially sweetened beverages than we do in water.
Wow. I did not know that.
Yeah. And so we do see changes that happen within the bacteria within our guts, but to this day, we cannot definitively say that those changes are good or bad. We just know that they are happening. There aren't any human-related health outcomes that stem from those things. There just aren't.
Cool.
Yeah. So that's where it is. I don't think I would be afraid of Neotame. I wouldn't be afraid of any of the other things as well. Let me see. I did see some stuff on, I think, sucralose that may, like if you're diabetic or pre-diabetic, maybe you want to maybe not use sucralose. Other than that, like,
Yeah.
fine.
Yeah. Yep. Yep.
Probably fine. Should you drink more water? Yeah, you probably should drink more water. Well, it's like,
Yes.
yeah, all right.
Just do it. Just do it.
That's
Wait,
it.
that's a slogan. Never mind.
Yeah, all right. So I hope somebody's mind was blown.
Mine was.
Take something away from this, and we'll see you guys next time. Coach Lambie and Dwayne out.